I'm now going to go through the solution for the Applied Maths Higher Level 2018 question 2, the relative velocity question. So we look first of all at the question for part A. We have an aircraft travelling at a given speed and it wants to fly directly from P to Q, where Q is north of P. And we're being asked what direction should the pilot set course for if there is a wind 60 kilometers per hour blowing from the northeast. So if we put that together in a diagram, we have our point P is south of the point Q. We want to fly, our actual flight of our airplane should be direct from P to Q, but we need to set off in some other direction, which I've shown here, heading off to the kind of northwest, and bearing in mind that the wind will bring us back down because the wind is, as it says in the question, the wind is blowing from the northeast, so it's from the northeast heading towards the southwest. So this is our vector diagram. We're being asked what direction should we head off in. We're looking for this angle theta that I've marked into this diagram. So some of the information that we have the velocity of the wind is coming from the northeast, so we can put in that angle of 45 degrees there, and we were told it's 60 kilometers an hour, so we can write the vector for the wind as minus 60 cosine 45 in the I direction, minus 60 sine 45 in the j direction. The actual velocity of the wind, we were told, that is the magnitude of it at least is 400 kilometers per hour. So we can write it using this diagram as 400 cosine theta in the I direction plus 400 cosine or sine theta in the j direction. We just don't know what theta is yet. Okay, we then have our formula which connects these two. So we write down our formula and we substitute into that. Now what we are actually wanting to do is fly direct from P to Q in a straight line. So our airplane actual velocity is only in the j direction. So we've worked it out here. We have an I and a j component, but we know that the I component must equal 0. Because going due north, there's no I component. So we can equate the I component to 0, and that will give us a cosine is 30 root 2 over 400, and I've just put that into a right angle triangle to model theta for me so that I can go back and find sine theta from that triangle. Okay, so I can also plug this into my calculator and find theta from it and give that into degrees, minutes and seconds using my calculator. So I need to quote this direction, so I can say that I'm heading east 83 degrees north. Alternatively, I can say I'm heading north 6 degrees south. Sorry, north 6 degrees east. Okay, so that's the direction that we needed to head off in. So then the next part of the question is, how far is the aircraft from P after 20 minutes? So we know that the aircraft is flying with this velocity of A that we calculated. We can go back and take our values and plug them in here. We know this is going to equate to 0. We know our sine theta from this triangle, so we can plug that in there and we can come up with our value, 355 kilometers per hour. And we were asked for how far did it get after 20 minutes, so 20/60th of an hour will give us our answer there. Part B then, we have a river which flows with a constant speed 4 meters per second. It flows between straight parallel banks, a distance 60 meters apart. And there's a woman with a boat, and she can row that boat in still water at 1 meter per second. So that is the speed of the boat relative to the water. We're being asked how long will it take the woman to cross from bank to bank, going across in the shortest time. So if we're going across in the shortest time, that's not the shortest distance. Going across in the shortest time is actually the longer distance, and making use of the flow of the river to bring you across faster. So we want to put the effort of the boat, the relative velocity of the boat, into going straight across, but the actual velocity will bring us to land downstream somewhere. So remember the banks were 60 meters apart. She could row this boat at 1 meter per second in still water, and the flow of the current was 4 meters per second. And we're being asked to find how long it will take to cross. So if we consider that her relative velocity is going across the bank here, which is 60 meters at 1 meter per second, that means it's going to take her 60 seconds. In part 2 then, we're asked to find the distance travelled by the boat when it crosses by the shortest path. So it's going to reach the nearest reachable point downriver on the opposite bank. So just to show you here, I've considered, normally we would think the closest point is the perpendicular distance going across, and I've just done the calculations here as if we were going perpendicularly across. If you try to resolve these equations, you end up with cosine of the angle is equal to 4, which of course is not possible. Maximum value for cosine is 1, so it's not possible to go directly across this river. We are going to end up slightly downstream. So I've redrawn the diagram showing where we are downstream, and I've put some measurements into this diagram. So I'm saying that we're going to cross this river in t seconds. I'm using the t method. The relative velocity is the one heading off to the left here. It's 1 meter per second. For t seconds, we'll travel a distance of t meters. The current will bring you back downstream at 4 meters per second. So over t seconds, you will travel back downstream for 4 meters or 40 meters. And the distance we're actually going to travel across is marked by d here. What we're looking to do is minimize the distance from the directly opposite point to where we actually do land. So this distance here needs to be minimized. And the way to do that is to, in fact, maximize alpha here that I've marked in. So alpha is this angle. These are alternate angles. So I've marked in alpha, and we want to maximize alpha. The bigger value we can get for alpha, the closer we'll be to that midpoint. Okay, so that's what we're aiming to do. So if we want to maximize alpha, we need to also then maximize sine alpha. And if I use this right angle triangle that I've marked in here, that we have alpha in this triangle, and we've a perpendicular distance across. So we can say that sine of alpha is given by this distance, is given by 60 over d. Sorry, I'm saying that incorrectly. But we can also use the sine rule on the full triangle. So on this whole triangle, we can say the sine of alpha over t is equal to the sine of this angle beta over 4t. And those t's should cancel out. So we will, we have an equation here where the t's will cancel, and that gives us an equation for sine alpha, which is what we're trying to maximize. Of course, sine alpha we can see here is given to us in terms of sine beta. So if we want to maximize sine alpha, we now need to maximize sine beta. And the maximum value for sine beta is 1. So the maximum value for sine alpha is going to be 1/4. So that's what we want to maximize. So as I said there a minute ago, sine of alpha is 60 over d from this right angle triangle. So we can use that information and we can say that that is equal to 1/4 because our maximum value of sine alpha was 1/4. So from that we can calculate the distance d to be 240 meters. So I'm just going to take a brief look at the marking scheme. So they have used, for part A, they've used the sine rule to calculate the angle, and then they've used the sine rule again to calculate the distance. So you can see the marks are given there each time for substitution and evaluating, and then for using the inverse sine function. And again, for in the part 2, they're given for the you need to substitute and evaluate, and then you need to actually calculate the distance. So that's part A, and then part B is the question for our river flow question. They have a similar triangle drawn. You get 5 for calculating the time going across, just substituting into the equation, and then 5 more marks for calculating the answer. In part 2, they've used the sine rule, and you get 5 marks for substituting into the sine rule, and then 5 marks for calculating the angle, and from there calculating the distance, another 5 marks. Okay, but you should be capable of saying this value of beta here is 90 degrees. Sorry, the reason that that is 90 degrees is because we maximized beta and we maximized sine beta, and that's where we got the 90 degrees from.